a little bit of a review here on what we've learned this week and also a little bit of new information. So the review on how computers work. Computers run on electricity. Electricity has two discrete states, on and off. We can store two messages with a single switch. We can store multiple pieces of information with multiple switches, and we can create coding schemes to represent what we're storing with a certain arrangement of on and off switches. So those are the core principles of what we've learned this week. And the last thing I want to show you, which is new information, is talk a little bit about the coding schemes for text, for images, for video, and for audio. Because everything that you see here, experience with a computer, it's all stored as zeros and ones. And so those zeros and ones ultimately have to have some coding scheme to say, hey, this arrangement of zeros and ones, or this arrangement of on and off switches, right, in a certain configuration, they represent this, or they represent that. So we've got coding schemes. So for text, we could say, hey, if the first light's on and the second one's off, that's the letter B, right? That could be the text coding scheme. For images, we could say, if both lights are on, that's this color, that's blue, or whatever. The main text coding schemes, ASCII, EBCDIC, and Unicode are the main text coding schemes that are out there. EBCDIC has been used for mainframes and IBM mainframes and IBM mid-range computers. That's where EBCDIC is used, right? The late 50s and early 60s. So that's kind of where EBCDIC was used. And then ASCII, character encoding scheme originally based on the English alphabet, encodes 128 specified characters. The numbers 0 through 9, the letters A through Z lowercase and A through Z uppercase, some basic punctuation symbols, some control codes, and dot, 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 dot. So, this was one coding scheme that was used for text. And here you could come down, you could actually see some zeros and ones and what those translate to, right? So here is, I don't know, here are some letters right here. The letter lowercase t is that arrangement of zeros and ones, or ons and offs. And then we have Unicode, and Unicode is a computing industry standard for the consistent encoding, representation, and handling of text expressed in most of the world's writing systems. So Unicode is like unifying the whole world. It's big enough to capture all of the characters in all of the different languages in the world. So Russian characters, Chinese characters, Japanese, Korean, English characters, right? And so Unicode captures all of those, those characters that are out there. So that's Unicode. So how do we take audio and turn audio? So we looked at text coding schemes. How do we, let's go to images first. How do we do it for images? How do we create some sort of coding scheme to store data for images? And what you'll hear is that there's sometimes this word bitmapped when you talk about image coding schemes. And bitmapped means you're mapping bits to the screen, basically. And on the screen, you have these things called pixels. And pixels are picture elements. Picture elements, that's what it stands for. Pixels is short for picture elements. So just think of this screen as a whole bunch of really small dots. And each of those dots could be a different color, right? So each pixel, each dot can be a different color. And we map, right, an image to all of those dots. And we say this dot's this color, that dot's this color. And when we get all those dots different colors, they make different images. So that's kind of how images are. And for each of those dots or each of those pixels, we have to store what color that one pixel is, right? And we do that for every single pixel. And so if we have just one bit allocated for storing the color of each pixel, so if our bit depth is 1 bit, we have 1 bit as our bit depth, that means that each pixel can be one of 2 colors. It could either be black or it could be green, or black or white. It could be one of 2 colors if we only have 1 bit. If we only have 1 light bulb, we can only store 2 messages, right? So if we have only 1 light bulb, we could store 2 messages. So with bit depth of 1, each pixel can only be one of 2 colors, right? It could either be this one or that one. If we have 2 bits as our bit depth, now each pixel could be one of 4 colors. So for each pixel, right, it could be, we're storing 2 bits of data. That's our bit depth, and that means that each pixel could be one of 4 colors. So the greater our bit depth, the more pixels, right, are stored. The more bits are stored for each pixel, but the richer the color becomes. So if we look at bit depth, right, in Wikipedia, color depth, there we go, also called color depth. Here is a 1-bit color. The bit depth is 1, so it's black or white. Here's 2-bit, so each pixel here could be one of 4 colors, right? Here is 4 bits, so each pixel could be one of 16 different colors. Here's 8 bits, so each pixel can be one of 256 different colors, and each pixel is a little dot, right? A little dot, a picture element. And here, if we have 24 bits for each pixel, so each pixel stores 24 zeros and ones, and it could be one of 16,777,216 different possible colors, and that's known as true color, right? For that many. So that's how we store data for images. For video, all video is a series of still images shown quickly. So it's very similar for video. And finally, coding schemes for audio. The way we store audio as zeros and ones. How do we do that? Well, it's very similar to the idea behind storing images as zeros and ones, in that we are going to, we're going to sort of take a really close look and then assign zeros and ones to really small aspects. So with the image, we took a really close look at the image. We broke the image down into a bunch of little dots or picture elements or pixels. And then for each pixel, we said this pixel's this color, this one's this color, this one's this color. And then we stored the zeros and ones, which represent each of those colors for each pixel. When we put them all together, we have an image. With sound, it's the same way. So with sound, there's something called the sampling rate, and that's measured in hertz, right? So sometimes you see 44.1 kilohertz for like audio quality. And that means that there's 44,100 samples of the sound taken every second. 44,100 samples taken every second. And so, in 1 second of audio, the computer has taken 44,100 samples every second. And when it plays back each sample, right, of sound quickly enough, it just sounds like sound to us. And so for each of those samples, right, it could store a bit depth also. Can it store one of 2 sounds? So the bit depth would be 1. It could only be this sound, or that sound, right? It'd be one of 2 sounds. Or can it be, is the bit depth 2, so it could have 4 sounds? So the greater the bit depth, the better the sound quality. And so that's how we have a coding scheme for audio. So the main thing to know, computers run on electricity. Electricity can be on or off, right? Ultimately, we are storing nothing but a bunch of on and off switches in certain configurations, which we abbreviate. Instead of saying on and off all the time, we abbreviate off as 0 and on as 1. And computers have that machine language, right, of zeros and ones. We call that the language of the machines, zeros and ones. And that everything that comes out of a computer or stored in a computer is ultimately the storage of these switches being in on and off states. So whether we're storing text or images or video or audio, all of that is ultimately stored as zeros and ones. So we have to find some way to represent all of these different things we want to store as zeros and ones. So we create coding schemes, right? So this configuration of zeros and ones means that it's this letter of the alphabet, or it means that it's this color, or it means that it's this sound, right? So that's kind of the start of understanding how computers work. And I know it's like, for me, it was mind-boggling. I was like, wow, are you kidding me? It's like so many zeros and ones. And that's the amazing thing about computers, is that they could actually process billions and billions, trillions and trillions and trillions of zeros and ones very, 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 very quickly. They could process them very quickly. And so then it just, instantly looks like the image came up. Sometimes you'll see with older computers, or back in the day, you know, the processing happens slowly and you actually see the image being formed line by line because the computer's just like grinding to bring it out. I don't know if you've ever witnessed that, but all right. So that's a little bit of a review of what we're learning this week. So I hope you got that nice and solid.